All right, let's finish section 4.4 by looking at the derivative of the logistic function that we just found. Okay, so off camera, I was actually kind of playing around with this function a little bit. I erased my previous work here. And so like I mentioned, it's a little bit of an ugly answer here because I'm trying to keep the solution exact. So that K number is that big ln, the big natural log mess. And there's a way to clean this up slightly, but I'm not going to clean it up for part B because when we take the derivative, it's nicer when you're taking the derivative of something that has a base of E. But if you recall, and you don't really need to write this part down, but just if we wanted to clean this up, there was a property that if you've got A raised to a log with the same base A of like something else, let me just call it like C, then the base with the log of the same base kind of cancel out and you're left with just that C number. And so technically that's what's happening with this E raised to the natural log. Those are both the same base. E and natural log has a base of E. So technically we could clean up the bottom right there a little bit, but it still has a T over 6 in the exponent. So we would be left with a situation something like that instead of an E raised to the power. Okay, and so it would make it look slightly nicer. However, when we take the derivative, it's easier to take the derivative of an exponential function with base E compared to an exponential function with a base different than E. Okay, so I was just playing around with this function a lot because yeah, it's definitely a crazy looking function and simplifying it in all kinds of different ways is something that interests me. So anyways, let's go ahead and just proceed with part B. We're going to find the rate of change of the rabbit population growth after 2 years and after 4 years. So there's two separate answers that we need, but they both come from finding the rate of change. And remember that rate of change is going to mean derivative. That means the instantaneous rate of change. Okay, so we need to find the derivative of that logistic function. And then once we find the derivative, then we get to plug in our values. Okay, so I'm going to write maybe a little bit big so that I can fit all of the nasty E raised to the ln power exponents. But here we go. This is going to be G prime of T equals. Okay, so how do we take the derivative of this big monster? Well, that's a giant fraction, and so I'm definitely going to need the quotient rule. Okay, it's not the only way to do it, but I'm going to use the quotient rule because it looks pretty obvious like we've got this giant fraction. Okay, so remember the way the quotient rule works, or the silly little way that I remember it, is low d high minus high d low all over low squared. Okay, so let's work that out. It's going to be low, which means the whole denominator by itself. Okay, so here we go. I'm going to leave myself some space here. So it's going to be the whole denominator by itself. So we have 1 plus 6249 e raised to this crazy thing. So there's the ln 4991 over 56241 over 6 t. Okay, so that's the low. Okay, then times d high, which means times the derivative of the numerator. So we got to go times derivative of 50,000. Well, that's nice because the derivative of a constant is 0. That's nice. That's going to wipe out that whole term. Okay, low d high minus high. Okay, so that's just going to be the 50,000. D low. Okay, so now it's the derivative of the denominator. So we got to be careful because there's a big mess down there, but it's really not quite as bad as it looks. So let's just go through and take the derivative of the denominator. Notice that it's 1 plus and then the big whole mess there. So we do the derivative separately. So the derivative of the 1, that's a 0 because it's a constant. Okay, so then we can just do the derivative of the second part. So the second part, it looks really nasty and messy because we're leaving it as this exact value, but all this really is, it's a constant times e raised to a function in t. And that function in t is just a constant times t. So there is going to be the derivative of an exponential, and then there's going to be a chain rule. Okay, so it's a constant times e to a power. So the derivative of a constant times e to a power is the constant times e raised to the same stuff, okay? The beautiful thing about leaving the base of an e, the derivative of e to the power of stuff is itself, okay? So let's write all of that, itself. Okay, but then remember the chain rule. We got to go times the derivative of the stuff. So the stuff that I'm referring to is the derivative of all of that function that the e is being raised to. And that looks nasty, but actually that big ln mess times t, that's just a constant times t. So if you're trying to find the derivative of like 5x, it's just 5. And so for this one, it's just a constant times the variable. So then it's just going to be the constant. So times the derivative of a constant times its variable, the derivative is just going to be the constant only. Okay, so then that's just going to be times, and we're going to have ln of all of that stuff. Okay, and then no t for this part because this is the derivative of that stuff. So the derivative of a constant times its variable is just the constant. Okay, and don't forget that we've done low d high minus high d low, and it's got to be all over low squared. So 1 plus 6249 e to the this stuff. So that's 4991 over 56241 over 6, and that's t. All of that is in the exponent of the e. And remember, it's all over low squared. So it's just leaving it all alone, and then it's squared. And so look at these nasty exponents on the e. And actually something just to mention kind of on the side, e gets raised to crazy powers a lot in advanced mathematics. And so look at how ugly that looks with all of the stuff from the e. Something that actually gets written because e gets raised to really crazy powers in advanced mathematics. Sometimes instead of having e raised to a whole bunch of stuff, I've seen it written as exp, like this. And that notation just means that whatever you put in those parentheses, it means that it's e raised to all of that. So that's kind of on the side. It's not something that we're going to really need to deal with in our class, but I wanted to mention, hey, a different way of writing e raised to a crazy power is there's this extra notation that I've seen, exp. But anyways, I'm not using that right now, but I just wanted to mention that e raised to crazy powers happens a lot in advanced mathematics. Okay, so let's clean this up a little bit. We've got g prime of t equals. So we're not going to go absolutely crazy with the cleaning, but there's a little bit that we can do. First and foremost, remember that this whole first term is just times 0, so it's gone. That's really nice. Okay, continuing on, this whole next section here is just a whole bunch of multiplication. So there's this 50,000. I'm going to keep track that it's negative, so maybe I'll put that right now. It's negative. And I'm going to want to leave some space. So let me erase that. G prime of t, write it a little lower. I want some space here. So yeah, I'm going to keep track that this is negative in the numerator. And then yeah, this is 50,000 times this 6,000 number. This e is raised to all this stuff with a variable. But then there's also times this constant thing in the back. So I'm going to do what I would normally do and just multiply all the constants together and then put that result in the front. Okay, so I'm going to get my calculator and I'm going to go 50,000 times 6,249. Okay, so that number right there. Okay, really big number. Okay, and then if I'm multiplying with this big ln constant thing, there is this divide by 6 thing. So I'm going to go divide by 6 in my calculator. And thank gosh that came out a whole number. Okay, this ln stuff of the 4991 stuff, that's still a constant, but I want to leave it exact. So I'm just going to go ahead. So what I've just done is I've done 50,000 times 6,249, and then I divided by 6. And with that negative in front, I got this 520 75000. Okay, that's all of that stuff. And then this ln of the 4999 stuff, that's also just a constant. So I'll just write that right here. Okay, so that's what I would normally do with all of the constants, is just multiply them together and put them in the front. Okay, and then the rest of this stuff is just that E right there. Okay, so now the only thing I need to write is this part. Okay, so then that's E raised to the craziness, ln 4991 over 56241. Okay, over 6, so all that's the exponent, and so is this t, all as an exponent. Okay, so that's about as much cleaning as we can really do, and then in the denominator, I'll just go ahead and leave it all how it was, 1 plus 6249 e raised to this stuff. Okay, so that's about as clean as we can really hope to get the derivative. Okay, don't forget that it's squared down there, okay? So yeah, that's about as clean as I really care to get it, because now what we want to do is plug in values. Okay, so what did this problem ask for? This is the beautiful thing about finding the derivative, is now we can find the rate of change for anything. So they asked us for 2 years and for 4 years, but we have to be very, very careful, because this was almost a trick here. Going back to the original problem, the units were months. Okay, so when we found in part A, we found this function, the t represents months. So for 2 years, that means how many months are in 2 years? 24 months, right? T equals 24 months. Okay, and then for 4 years, we have to do t equals 48 for 12 times 4. Okay, so watch out for that. That's almost a trick right there. 2 years and 4 years, we need to make sure we have it in months. Okay, so it's a little bit of a hassle to try to type all of this into the calculator. I'm going to do it right now on the spot, and I'll just kind of say it out loud exactly how I'm doing it. So we want g prime of 24. So this is the 2-year rate of change. And now I'm not going to write it all down again, but I am going to try to just type it all into the calculator at once. Okay, and this is, if you're feeling a little bit daring, then you can go ahead and give this a try too. I'm going to show you exactly how I'm typing it in with extra parentheses and just being very, very careful with how I type it into the calculator. If you use like your phone for this, it would be almost impossible. So I definitely recommend to use your scientific calculator. So as I type this in, I definitely want to use extra parentheses around the entire numerator, just so that my calculator doesn't get confused. Okay, and then another thing that I want to do is use extra parentheses around the exponent on that e. Okay, same with on the denominator, I want to use extra parentheses around that entire exponent on the e. Okay, otherwise the calculator can get very confused because it uses the order of operations very specifically. Okay, so here we go. I'm just going to type this into my calculator, and I'm going to just say it out loud of what I'm doing. So here we go. For g prime of 24, keep track that we're going to be replacing the t in both of these spots with a 24. Okay, so that's also what I'm going to be doing. Okay, so here we go. I'm going to start with parentheses, negative 52075,000. Okay, then natural log. It creates its own parentheses, 4991 divided by 56241, close the parentheses on the natural log. Okay, then I'm going to write times e raised to the parentheses, natural log, which creates its own parentheses, 4991 divided by 56241, close parentheses on the natural log, divide by 6, times the t now, and the t is a 24. So I'm typing 24 for t. Close parentheses on the exponent of the e, close parentheses on the whole numerator. Now I press divide, new parentheses for the denominator. Okay, so now I'm down at the denominator part. 1 plus 6249 times e raised to the parentheses, natural log, which creates its own parentheses, 4991 divided by 56241, close parentheses on the natural log, divided by 6 times, and again, t is 24, so I type 24, close parentheses on the e exponent, close parentheses on the denominator, and then make sure I go squared for the denominator. Now I press enter, and the number that I got is 4062, and I'm going to use all of the decimal places because we were awesome keeping track super specific. So 0.88316. This is the whole number that my calculator gave me. And what did we just find? This is the rate of change of the population growth, and the units are months. So this is 4,062 point whatever rabbits per month. Okay, that's the rate of new rabbits. So at exactly 2 years, we have an increase in rabbits of a rate of about 4,000 rabbits per month. Okay, so G prime of the 4 years is G prime of 48. Okay, so this one is the 2 years, and this is the 4 years. Okay, yeah, so those rabbits, I mean, they're going crazy after 2 years, an extra 4,000 per month. And look at where we started. We started with 8 rabbits. And so after 2 years, there's another 4,000 per month showing up. Okay, after 4 years, and just to save some time, I actually typed all of this in earlier. And being very, very careful in the same way, everything was the same, except this time I replaced t with a 48, and I got this, 0.48513275. Okay, and this is also rabbits per month. Okay, so what in the world do you think this means? Because that's a really strange answer. If you got that answer on your calculator, you might think you did something wrong, okay? Now this is not wrong, I checked it a couple of times, okay? I really wanted to make sure. But yeah, this is the answer to the problem, the G prime of 24. So yeah, after 2 years, the rate of growth was 4,000 rabbits per month, okay? But after 4 years, the rate of growth was like less than a rabbit per month. Now, what the heck is going on there? Now, like I said, with logistic functions, there is like a period of time, and we wrote that on the previous page here. Population starts growing slowly, then it goes more rapidly, but then it gradually levels off. And that's more realistic based on finite resources and all of those kinds of concepts. So it looks like after 2 years, the rabbits were going crazy. But after 4 years, they're actually kind of reaching their limits. They can't really have too many more rabbits showing up per month because this is a period of time when maybe it's actually approaching that 50,000 level, right? The island can't handle more than 50,000 rabbits. So that's actually kind of an interesting result. And so it did say, what do these rates tell us? And so I'm kind of saying that out loud here. After 2 years, the rabbits were increasing at a rate of 4,000 per month. But after 4 years, it did seem like we're reaching that carrying capacity of the island. It can't handle too many more rabbits per month. And so after 4 years, it's flattening out, and the rate of increase of new rabbits is now less than 1 per month. Okay, so yeah, that's the answer. Here are the 2 different answers for this. And then let's definitely click on this. I've got Desmos with everything all filled out already right here. So let's click on this and explore these answers with Desmos. Okay, so it's right there. You can click on that same link and you can get to this exact same setup that I have here. So I've got the G of t function plugged in there. So we did all that work and I wanted to keep it exact so that the Desmos gave me exact values. Okay, so here's that nasty G of t function with everything just like we did it from part A, okay, with that weird K number that we found. I added a slider here for a where we can find g of a for whatever number. And so at a equals 0, it's telling us that it comes out 8. And that is consistent because that is at time 0, the initial amount is 8. Okay, so that's consistent. And so if we slide this around, we can also see what the amount would be. So g of a tells us how many rabbits are there. So if I move over, and these are months, okay? So right, every time t is increasing, these are months. Once we got to month 6, that's the 90 number. And again, this is why I wanted to keep this exact, because otherwise these numbers would end up being decimals that are a little bit off. And remember that after 6 months, it was 90. Okay, so our function is looking pretty good in terms of the actual real model. And then as we let the months go by, notice how the number of rabbits starts increasing very quickly, right? And it's like this exponential kind of curve that we're used to seeing. But then once a certain number of months start to go by, it starts flattening out. And that's what is happening with these logistic functions. You end up with some kind of a limit here where you're approaching what's actually this horizontal asymptote at 50,000. Whatever that maximum number was, that's actually a horizontal asymptote. And so as time goes by, so this is the number of months, it's approaching that 50,000 number. And so you can see the G of A numbers there. It's approaching the 50,000 number, but it won't ever reach it. Okay, but there's a period of time at some point right through that range of months right through here when it's really steep, right? The rabbit population, as you can see labeled on the y-axis, they're going up very quickly, very, very quickly. Okay, and then some of the beauty of Desmos here is I also have g prime of a. Okay, so this is actually calculating the derivative for us. Now, if you were actually going to work out these problems, you do need to show your work. Okay, so all of this process we did by finding the derivative, we have to show our work to find that. But if you want to check to see if these answers are right, especially since typing it into the calculator is a little bit tricky, then I invite you to use Desmos. So I have g prime of a right here. And what did we want? We wanted 24 months, right? 2 years. So if I set A at 24, that would be the 2-year mark. And G prime of A, which tells us the rate of change, the instantaneous rate of change, here's that 4,062.88 number that we got when we typed it in, 4,062.88. That's what we got when we typed it all into our calculator, okay? Pretty cool, and that makes sense. Look how steep the function is right here. And actually, I went a little bit further just for fun, and I put this right here, which would be the tangent line. Okay, and so yeah, look how steep that is right there. And you can see as we're dragging this function around for different month values, it becomes steeper and steeper and steeper where the rate of change is really, really big, but then it starts to level off. And then it's less of a steep slope, which means the rate of change is less and less and less. And so if we go all the way out to 48, which was the 4-year mark, look at how almost flat that's getting. And then for 48 months, there's the G prime of 48, and looks like we get 0.485 something something. And so 485 something something. So that is a visual representation of what's going on. Once we hit 48 months, we're really, really close to the maximum carrying capacity that this island can have. So the rate of change of new rabbits per month can't be very much anymore, okay? Right around this level here, there's a lot of rabbits reproducing, there's a lot of resources, and look at the rate of change. I mean, 5,000 rabbits per month at month 22. Okay, so as you're noticing, notice that the rate of change increases. There seems to be some moment right in this monthly range here where the increase is the biggest, and then it starts to flatten out again. And so a natural question is, well, where was that moment when the rate of change was the largest? There seems to be some moment through here when the slope of the tangent line or the rate of change of this function is the biggest. And that's actually a very, very important topic in differential calculus. And we're going to come back and actually explore that topic with different types of functions in chapter 5. Okay, but for right now, we don't know where that maximum moment is. All we knew was at month number 24, pretty steep rate of change of those rabbits. And then over at month 48, the rate of change is not very big because we're approaching that maximum carrying capacity. Okay, so definitely a crazy problem. Most of the time, if you were given a problem like this, you would probably be told what the K value is without having to find that big nasty LN number on your own. Okay, so just keep that in mind. I wanted to do an example that was about as hard as these problems could ever be in the lecture, rather than doing an easy one in lecture and then having you struggle with one if you saw it on the homework. Okay, so anyways, that finishes off section 4.4. Hope you have a good day.